This is Aerodynamics Podcast number 14, and we're talking about the aerodynamic ground effect of fruit fly flight. So this is pretty cool because in number 9 of our podcast, we talk about the ground effect of aircraft, and in number 12 podcast, we talk about insect flight. So these two topics sort of get merged together in this podcast. And to look into it, we're going to be looking at this paper called Aerodynamic Ground Effect in Fruit Fly-Sized Insect Takeoff. And in this paper, they model a fruit fly in CFD. And they talk about how this differs and is similar to a rotary aircraft in ground effect. So they start off with the abstract and they say, in recent studies, there's a contradiction in results in terms of whether the ground effect of an insect is positive or negative in terms of lift. And some even have zero ground effect. So in this study, they look at a numerical study of fruit fly-sized insect takeoff with a specific focus on the significance of leg thrust and wing kinematics. So the leg thrust, they look into how much the insect jumps off the ground and propels themselves into the air. And then the wing kinematics, so how much the wing is actually moving up and down. And they modify that to see how that affects the ground effect. And they also look at only 2 degrees of freedom, so the vertical and the longitudinal horizontal displacement. So those are some limitations of this paper. This was done in 2016. And they go on and say the parameters of the model are then varied to explore possible effects of interaction between the flapping wing model and the ground plane. These modified takeoffs include cases with decreased leg thrust, so the insect isn't jumping as high into the air, and or periodic wing kinematics, constant body pitch angle. The results show that the ground effect during natural voluntary takeoff is negligible. So when an insect just jumps off a fruit fly, just jumps off the ground into the air, as a regular takeoff, there's negligible ground effect. In the modified takeoffs, however, when the rate of climb is slow, the difference in aerodynamic forces due to the interaction with the ground is up to 6%. However, depending on the kinematics, this is either a positive or a negative effect. And this is in contrast to the helicopter theory in ground effect, which suggests a positive excess lift. So in other words, compared to a rotary aircraft in ground effect, which is always going to experience a positive ground effect, an insect with these modified parameters, so the modified wing beat and leg thrust, can experience either a positive or a negative effect. And they say that this is probably because of an unsteady wing-wake interaction. They also considered hovering, and they go into that a little bit as well. So in the introduction, they say, although the effect varies depending on many design parameters, the general trend is that an increase in lift at pitching moment and a decrease in drag occurs in ground effect, for aircraft at least. And as you go further away from the ground, this benefit decreases, so you don't no longer get an increased lift pitching moment or a decreased drag, and you go to regular flight. For example, for a hovering helicopter, the excess thrust vanishes if the distance to the ground exceeds 1.25 times the diameter of the main rotor. And a normal hovering in ground effect was considered by Gao and Liu, so another paper, and they carried out 2-dimensional numerical simulations of hovering and identified 3 regimes: force enhancement, force reduction, and force recovery for insects in ground effect. And this depends on the distance to the ground. In another paper, Liu and others considered clap and fling near the ground and found force enhancement at all distances. So clap and fling is a way that a lot of insects do fly, for example, fruit flies and butterflies. If you want to know more about that, look at podcast number 9 of ours. We go into that. And the 3-dimensional simulation of fruit fly hovering was carried out by Maida and Liu, and they found that an increase in lift and a reduction in power occurred. So there's quite a bit of contradiction in terms of different results, which are affected by the different parameters that you look into, and we'll get into that in a second. And they go on and talk about other studies. So several studies considered pitching plunging foils near a solid wall or a free surface. This configuration is relevant to fish swimming as well as forward flapping flight. So that's pretty cool because fish, they are near surfaces often and near the ground and near walls, and they swim along. they have a similar kinematics and they can experience similar effects. So the main motivation for this study comes from the fact that the ground proximity is natural for takeoff and landing. These maneuvers, unlike hovering or forward flight, are characterized by gradual change of distance to the ground. The dynamic ground effect in these circumstances may be different from the static effect at constant distances. So what they're saying is, if you have an insect and it's on the ground and it jumps up, there's obviously a dynamic effect there where it's going from the ground to significantly higher. Whereas if you're in hovering, then you're just static. You're at a certain distance from the ground and you're always at that distance. So it's, I guess I don't know if it's static, it's probably more quasi-static, but that's the difference. And this difference may be even larger for flapping wings than for fixed wings, because animals vary their wing kinematics during takeoff, which is pretty cool. And you can actually hear that with pigeons. If you're ever in a park and there are pigeons around, just listen to when they take off. You can hear this clicking, like it's like something slapping together. And as they get into regular flight, you don't hear that anymore. That's because they've changed their wing flapping, how they flap. And insects do it as well, and etc. So far, the ground effect during takeoff has been assessed for very few insects only. It was found negligible for butterflies, a dronefly, and a fruit fly. However, it was significant for a beetle. And then they go on and say that their work is motivated by the apparent contradictory conclusions of the significance of the ground effect that could be found in the animal flight literature. And in the present study, they consider a numerical model having the morphology of a fruit fly with rear wing kinematics and leg parameters. So they looked at, as I said, how much they jump into the air and how much they actually beat their wings. And then they go on and they just talk about, they sum up their results first of all. So let's go through this, and it gives you most of what they found. The starting point of our study is the voluntary takeoff. So this is how an insect usually takes off. As it is shown in section voluntary takeoff, that the ground effect is very small in that case. And with the voluntary takeoff, they just go on and say that some important general features of fruit flight takeoff, such as the first wing beats beginning while the legs extend. So as they're jumping off, obviously they beat their wings a little bit, and they found that there was no ground effect. And then they go on and say that they conjecture that this difference, and then in flight, they found a little bit, and they said that they conject that this difference is due to the large takeoff vertical velocity, which is mainly the result of leg thrust. To test this hypothesis in section slow takeoff, we discuss a situation in which the legs produce less force and the insects take off slower. So they want to see if the insect takes off slower, it spends a greater amount of time near the ground, if there's a greater ground effect than if they just jump off regularly. And they found that the ground effect then becomes significant. The vertical force increases during the first two wing beats due to the ground effect, but slightly decreases later on as it gets further away. They then carried out a parametric study using periodic wing kinematics in section takeoffs and with simplified kinematics, and find an even stronger adverse ground effect. So that's interesting here that they said it's adverse ground effect. So in this particular case, the ground effect was bad for the insect, which is probably why they jump off faster. Finally, in the section ground effect in hovering flight, they found similar trends during the first wing beats in hovering flight, which can be considered as a limiting case of takeoff with zero rate climb. So they went through and they looked at all these different studies and all these different situations where the wing insect is taking off. One thing that I want to point out is, so this paper was done in 2016, and about a couple of years ago, it started to become fairly well known that a lot of insects, for example, fruit flies, which is the insect they're looking at here, when they take off or when they flap even, they bend their wings a little bit and the wing flexes, and that significantly affects the lift of the insect. So if you have a very straight wing, the vortices that come off the wing, which is what they utilize a lot to lift, they aren't captured as well as if you have a bent wing. And through evolution, they've obviously developed this. So in this study, because this was before we even knew about this particular case that they do bend their wings. They were, from what I can tell, they were only looking at straight wings. So the wings were not bending at all. So that means that there is some difference between an insect and this model. However, how much the results then map onto it is probably still pretty good to some extent. So that's one thing that they could look into further. If you have a flexible wing where it is bending, they might have a different ground effect during takeoff, during a regular takeoff. And then they go on and they just say that they found that the ground effect during the natural voluntary takeoff is negligible. The wing beat average forces only differ by less than 1% of the weight. The aerodynamic power difference is less than 0.5% during a regular takeoff. However, when they modify the takeoff, so they decrease the leg strength, which means that the animal isn't jumping up as high, the rate of climb decreased as such, and the ground effect became significant. Surprisingly, the vertical force did not always increase. It even dropped in some of the cases that were considered. This is an unsteady effect related to the vortex rings bouncing off the ground surface. To better understand the mechanism of the adverse ground effect, we considered hovering near a flat ground surface, being the limiting case of zero rate climb. In that case, the fountain effect produced a large upward force on an insect's body. Now, just here, I want to talk about the fountain effect. I looked it up a little bit because I don't talk about it in this paper. And what I couldn't find too much, but I assume that it's probably quite similar to the helicopter fountain effect. So, and what happens there is you have all this air being thrust into the ground, and then it sort of rebounds up. So if you do know this fountain effect, drop it in the comments, because I'd be interested to know as well, know exactly what it is. But I think that's what it is. I think they're using the same an analogy for rotating aircraft. And so anyway, they go on and say the net ground effect was therefore positive for a zero rate climb effect when the insect is just hovering. However, the aerodynamic force acting on the wings in ground effect was sometimes less than when the wings operate out of ground effect. The most significant decrease was observed during the first 15 wing beats. Note that this is a much longer time period than a typical takeoff. At long time hovering, the effect was either positive or negative depending on the wing kinematics. And here what they talk about is, what they mean is in their research, they looked at obviously the regular beat of the insect's wings. However, they also looked at when they reduced the amplitude of that, and they found that that was actually a more beneficial situation. Now, whether insects reduce their amplitude during takeoff or not, who knows? But they looked at that in this paper. So the parameter space in the takeoff problem is very large. In this present study, they focused on the leg thrust and wing kinematics. However, the ground effect may also be sensitive to the Reynolds number, which is really interesting, because the structure of the wake at higher Reynolds number is significantly different from that of a lower Reynolds number. So that means that if you have a bigger insect or it's taking off with a gust, the ground effect may be different, and that's probably going to be the case when an insect is optimized for its entire lifespan, so not just one small section of flight, unless it's due to hunting or whatever. So that's the end of this podcast. Make sure to like and subscribe. Check out our aerodynamic instruments to make your experiments better. Check out the courses we do to make you a better aerodynamicist. And check out the International Aerodynamic Conference. It's a conference we put on every year for aerodynamicists, and it's there for everyone who loves aerodynamics. So we'll see you there. Peace out.